Introduction to Confidence Intervals. Lesson objective: obtain a point estimate for the population proportion. The heart of statistics: inference from samples to populations. Statistical inference facilitates a decision making. Lesson objective: now we will begin our work in statistical inference. That is, we're going to take information obtained from a sample to make inferences about a population. This is the heart of statistics. There are two main branches of statistical inference: confidence intervals, which is also known as estimation, and hypothesis testing, which is also known as test of significance. One aspect of inferential statistics is estimation, confidence intervals, in which the process of estimating the value of a parameter from information obtained from a sample. So let's review what's parameters and what's statistics. A statistic is a numerical value coming from a sample. A parameter is a numerical value coming from a population. So if you recall, X bar is our first example of a statistic, and it can estimate the population parameter mu. So this is an average, but this measures a population mean. This is a sample mean. Another example of a statistic is S, the sample standard deviation, and it can be used to estimate sigma, the population standard deviation. This is p hat. It is a statistic. It is what we call the sample proportion, and it estimates what we call p, which is a parameter, which is the population proportion. So let's start off with a definition. A point estimate is the value of a statistic that estimates the value of a parameter. We will begin with the estimation of p, the true population proportion. P hat, which is denoted by this symbol, is the sample proportion, and it is our best point estimate of the true population proportion p. So we're going to use p hat to estimate p. A point estimate is an unbiased estimator of the parameter. The point estimate for a population proportion is p hat equals x divided by n, where x is the number of individuals in the sample with the specified characteristic, and n is the sample size. Let's look at an example. Here's an example of a poll from Gallup. It's the president's rating, and we see here that there is actually two p hats. One p hat for the percentage that approve of Obama, so that's a p hat, and then we have another one for the percentage that disapprove of Obama. Now Gallup tracks daily the percentage of Americans who approve or disapprove of the job Barack Obama is doing as president. These are based upon telephone interviews with approximately 1,500 national adults. Margin of error is plus or minus 3 percentage points. So we'll talk about margin of error a little bit in this video and in future videos. So if we look at 49%, this p hat, this is the sample proportion who believe Obama is doing a good job. And what this is trying to estimate is the population percentage who believe Obama is doing a good job. Now, of course, it would be very time consuming, very expensive to try to ask every single American adult. So we're going to use this p hat along with the margin of error to estimate the population percentage who approve of the job Obama is doing as president. Here's another poll. This is by CNN. The sample was 700. And again, here we have a p hat for approve and a p hat for a disapprove, and they also include a margin of error. So this is a p hat, and if we include our margin of error, that is what is going to make a confidence interval. And of course we know that when we take multiple random samples from a population, it will yield multiple values of p hat, and each one is a valid estimate of the population proportion p. So this implies that any single estimate of p is unlikely to be exactly correct. We call this sampling error. So every time we do a sample, we expect p hat to change a little bit. And so we also need is a range of values that we can expect that would capture the true but the unknown value of the population parameter. This range of values is called a confidence interval. So a confidence interval is our point estimate plus or minus what we call the margin of error. Why do we need a confidence interval? Well, a point estimate by itself is not sufficient, as it does not tell us how close the estimate is likely to be to the parameter. A confidence interval is more useful. It incorporates a margin of error, so it helps us to gauge the accuracy of the point estimate. Let's look at a visual. Here's a point estimate, p hat, 0.73, and this is our best guess for the parameter. Now, an interval estimate, which is the same thing as a confidence interval, is a range of numbers that we believe the true population parameter to fall within. So if we start with our point estimate, p hat, if we subtract what's called the margin of error, we get what's called the lower limit. And if we take p hat and add the margin of error, we get what's called the upper limit. And this is what we call a confidence interval. So you may ask yourself, how do we compute this margin of error? Well, the margin of error depends upon a number of things, and we are going to look at some formulas for the margin of error in future videos. Significance level. We are going to define a quantity, Greek letter alpha, in which we call the significance level. We'll have more to say about what the significance level represents, but for now it's enough to say that alpha is a number between 0 and 1, and as we'll see later, common values for alpha are 0.01, 0.05, and 0.10. Now the quantity 1 minus alpha is what's called the confidence level, and this is the first thing that can affect how large the margin of error is. Thanks for watching.